what actually makes something a vector, and what makes a whole collection of vectors a vector space. Let's build this up from the ground. A vector in the real numbers to the n is simply an ordered list of n real numbers, written as components in a row or a column. Two operations matter most here: vector addition, where we add component by component, and scalar multiplication, where we multiply every component by the same number. Let's work a full example. Let u equal the vector 2 minus 1, 4. Let v equal the vector 3, 5, minus 2. And let c equal minus 3. First, u plus v. We add each pair of components, 2 plus 3, minus 1 plus 5, and 4 plus minus 2, giving u plus v equals the vector 5, 4, 2. Next, c times v, we multiply every component of v by minus 3, giving minus 3 times 3, minus 3 times 5, and minus 3 times minus 2, so c times v equals the vector minus 9, minus 15, 6. Finally, u minus v, we subtract each component 2 minus 3, minus 1 minus 5, and 4 minus minus 2, giving u minus v equals the vector minus 1, minus 6, 6. Now zoom out to the bigger idea. A vector space is any set equipped with addition and scalar multiplication that satisfies 10 axioms in total. The two axioms that matter most in practice are closure under addition, meaning adding two vectors in the set gives another vector still in the set, and closure under scalar multiplication, meaning scaling a vector in the set gives another vector still in the set. Now consider a subspace, a smaller vector space sitting inside a bigger one. To prove a subset W is a subspace, we check three conditions. It must contain the zero vector, it must be closed under addition, and it must be closed under scalar multiplication. Let's test this on a specific example. Let W be the set of all points x, y, z in the real numbers to the 3, satisfying x plus 2y minus z equals 0. First, check the zero vector. Plugging in x equals 0, y equals 0, z equals 0, gives 0 plus 0 minus 0 equals 0, so the zero vector is in W. Next, check closure under addition. Take any 2 points in W, satisfying the plane equation, and add them component by component. The sum still satisfies x plus 2y minus z equals 0, because the equation is linear, so the sum stays in W. Finally, check closure under scalar multiplication. Take any point in W and multiply it by a scalar c. Since the equation is linear, scaling every component preserves x plus 2y minus z equals 0, so the scaled point also stays in W. All three conditions hold, so W really is a subspace of the real numbers to the 3, a whole plane through the origin behaving exactly like a vector space in its own right. Like and follow for more math tutorials, one idea at a time, nothing rushed.